Let's take a look at an example of a perfectly inelastic collision. We're going to have a 3 kilogram object on the left moving with 2 meters per second east. That object's going to collide with a 1 kilogram mass moving with 2 meters per second to the west. Now, if these objects collide and stick together, what will be the magnitude and direction of the final velocity of that mass? So let's just combine them here in the center at a later time. It's going to have a total mass of 4 kilograms. In order to conserve momentum, which way do you think the 4 kilogram object will be moving after the collision? We'll find out through calculation. First, we have to find the initial momentum of the 3. We'll call it P3I. We want to use the mass of the 3 kilogram object times its velocity. And that'll be the initial velocity. Then we'll find the initial momentum of the 1 kilogram object. Okay, let's calculate them. Momentum has the units of kilogram meters per second. Let's find the other one's momentum. You do want to consider the direction when you work with momentum. Okay. So what we see here is that our sum of momentum initially is 6 kilogram meters per second minus 2 kilogram meters per second. That's 4 kilogram meters per second. What we need is we need the initial momentum to equal the final momentum. So the final momentum also needs to be 4 kilogram meters per second. Now let's calculate the final momentum of that 4 kilogram object. It'll be the mass of it times its velocity. Since it's the only object left because the other two have consolidated themselves into it, it needs to have 4 kilogram meters per second of positive momentum. That means it's actually going to end up moving to the right. And that should make sense because if you look at the setup here, the 3 kilogram object is going to basically win out in the collision. It's going to overpower the 1 kilogram object. If they had been equal masses, it would have stopped dead right in the middle. But the 3 kilogram object carries with it much more momentum, so it's going to win. Let's figure out now how fast the 4 kilogram object will be moving. We just have to divide and it's positive 1 meter per second to the east. Now we know. That's an example of a perfectly inelastic collision. Now, one thing that's interesting here is notice that the objects didn't lose all their kinetic energy. It's actually not required for them to lose all the kinetic energy, but they do have to lose as much as possible in a perfectly inelastic collision. So if we were to just kind of quickly find the kinetic energies at the beginning and at the end, we could see the change. So K3I would be 1/2 times the 3 times 2 squared. That would give it 6 joules. And K1I would be 1/2 mv squared, so 1/2 1 times 2 squared. K1I would be 2 joules. Okay, so our sum of kinetic energy at the beginning is clearly 8 joules. How many joules does it have at the end? 1/2 times 4 times 1 squared, which is 2 joules. So although we started with 8 joules of kinetic energy, at the end, our object only has 2 joules of kinetic energy. So where did the other energy go? Well, it could have gone into motion of the particles themselves, and I mean the microscopic particles inside the object. It could have warmed up the object, and it could have been converted into thermal energy. We also could have had sound, vibration, rotation. The energy could have gone into many places, but it's not in kinetic energy anymore. And that's the key to an inelastic collision, is that the kinetic energy gets changed into different forms.